solving of major test 7 doubts or anything like that. Okay. Also, I think you will be sent the solutions, so don't worry about that. So let's begin with today's session.
Excuse me, so can you
Yes.
please repeat the last second sentence that you said? I mean, the Zoom meeting had said the recording has started now, so we couldn't hear what you said.
Oh, I didn't say anything. I just said that we'll start a new chapter today.
So before that,
Yeah.
so you
Just
said that
much.
you said what we, so after the gap what we heard was that you will be given the solutions.
Yeah, major test you will be sent some solutions also, so don't worry about it. So we'll start with the next section of physics, which is fluid mechanics today. So this is a comparatively easier section of physics, fluid mechanics and properties of matter. The last part of class 11th before we'll start with the 12th chapters.
Sir,
Yes.
excuse me, sir. Sir, heat and thermodynamics entire part was comes in 12th, right?
No, it does not actually. It comes in 11th.
Okay, fine.
In HC Verma, it is in part 2, but in NCRT curriculum, it comes in 11th.
Okay, sir.
Okay, so now about fluid mechanics, the first part is called hydrostatics, which, as the name suggests, is to do with the fluid at rest. So hydrostatics is about the physics of a fluid, but in this case, we talk about something called an ideal fluid. So an ideal fluid at rest, what we call static. Now the question is, what is an ideal fluid? So an ideal fluid has two important properties. A fluid which is, first of all, incompressible. Okay, so that means cannot be compressed. So what that literally means is that its density is uniform and independent of pressure. So such a fluid is called incompressible. Okay. So it is firstly incompressible, and secondly, it is what we call non-viscous. So non-viscous means that its viscosity is negligible. And what we mean by viscosity in fluids is the drag forces that act when there is relative motion. So viscosity or viscous forces are drag forces which oppose the relative motion, like friction in solids. The equivalent of that in liquids is called viscosity. So an ideal fluid is one which is non-viscous. So if the viscosity is negligible or it's almost absent. So water, unless subjected to extremely high pressure, is an example of an ideal fluid. Is whatever we learn in this chapter about a fluid at rest, it will be with the assumption that it is an ideal fluid. That means it is having uniform density independent of pressure, and viscosity in it is absent. Okay.
For 1 minute, please.
So please, can please pull it up. Thank you.
Okay, done.
Just
For
a-
1 minute, please.
Okay, so let's move on to understand the first important set of properties of an ideal fluid at rest. So if we consider an ideal fluid at rest in a container like this, and it's at rest in the ground frame. So the container is at rest with respect to the inertial frame, or what we call ground frame. Then the most important aspect of this is how the pressure varies with depth inside a fluid. So this is some ideal fluid which has a density equal to rho. We generally use the symbol rho for density. So density is expressed in kg per meter cube, okay, or gram per cc. And you should remember the conversion that 1 gram per cc is equivalent to 10 raised power 3 kg per meter cube. Density of water is about 1 gram per cc. Density of ice is about 0.9 gram per cc. Density of something like, let's say, kerosene oil is approximately about 0.8 gram per cc. Density of mercury is 13.6 gram per cc. Okay. So these are some of the standard values. You don't need to memorize them. Okay. So this is a tank which is stationary with respect to ground plane. So if we are taking our system of axis such that the vertical is our y-axis and the horizontal is our x-axis, then what we will see is that pressure varies inside a fluid such that what we call vertical pressure gradient that is change in pressure upon change in vertical coordinate is given by the formula minus of rho into g, where g is acceleration due to gravity and horizontal pressure gradient delta p by delta x is equal to 0 in this kind of a situation. So here g is acceleration due to gravity. So pressure, as you can see, increases with depth or it decreases with vertical height. So we have a negative vertical pressure gradient, and with horizontal displacement, pressure does not change. So hence delta p by delta x is 0, where x is the horizontal axis and y is the vertically upward direction axis. So this is an important property for any fluid, first of all, which we should understand.
So,
Yes.
so that
Sir,
one, sir, it should be 10 raised to 3 gram per cc.
No, it is not that better. You can check your concepts of units and dimensions. It's quite easy to prove this. Okay. 1 gram is 1,000th of a kg, but 1 cubic centimeter is 1 millionth of a meter cube. You have learned all this in the chapter of units and dimensions, how to convert one unit to another.
Yeah.
excuse me, sir. Sir, why is delta p by delta x equals 0?
Because that is the property of a fluid, that if you take 2 points which are on the same horizontal plane inside the fluid, there is no pressure difference between them.
Okay, okay, okay.
2 points at the same depth have the same pressure. So
Yeah,
moving along the x-axis, there is no change in pressure. So that's why the gradient, that is rate of change of pressure with respect to horizontal displacement, is 0.
okay, got it, sir. Thank you so much.
Okay. So pressure is basically what it is, normal force per unit area acting on any surface inside the fluid at a given point. So it is normal force per unit area acting on any surface at a given point. Okay. So pressure is measured in Newton per meter square. Okay. SI unit is that, or pascals. So 1 pascal is equal to 1 Newton per meter square. We will also understand the barometric unit of pressure, which you might have I mean, which you've seen in thermodynamics and all, atmospheres or bar, or sometimes we also express it in terms of height of mercury column. So we'll see how to convert those also in terms of pascals. We understand the working principle of barometer also. So all that actually comes from this explanation, that pressure gradient, the vertical pressure gradient is a negative constant. Why constant? Because obviously density is uniform in the fluid, it's an ideal fluid, and horizontal pressure gradient is zero. Okay, so now again, to visualize
1 minute.
pressure at a point inside the fluid, okay, what we have to do is, like, imagine again in the container, we are talking about pressure at a point like this. So imagine a small imaginary surface of area dA. So that surface will be experiencing a force because of the liquid normal to it. So because that surface area is very small, so the force will also be very small. So the pressure at that point will be that normal force delta F divided by the area delta F. Okay, so this is like a way to mathematically understand pressure at a given point, where delta A is a small area element, okay, at a point, and delta F is the normal that means perpendicular to the surface, okay, normal force applied by the liquid on it. So then P becomes the pressure at that particular point. So even though there might be no actual surface physically present at the point where we are calculating the area, where we are calculating the pressure, but if we imagine that there's a small surface, okay, which is present at that particular point, so that surface would be experiencing a force going into it, going perpendicularly into it. So that is what we mean by the term normal force. So that normal force divided by the area, that is the quantity we measure as pressure. So hence it is measured in newtons per meter square or pascals. And also another important thing is that pressure is a scalar thing, because even though we are writing it as force per unit area, it's a specific component of force. It is normal force. That means force perpendicular to the area. So a component of a vector is not a vector quantity, it's a scalar. Hence pressure is a scalar. So additionally, you should understand this thing, that pressure is a scalar quantity. One more thing we should understand here, that for density, sometimes we use the term relative density, or we also call it specific gravity. So this relative density or specific gravity for some material, it is defined as density for that particular material divided by density of water. So for example, relative density of mercury is 13.6, because we know that density of mercury is 13.6 gram per cc and density of water is 1 gram per cc. So actually whatever is the relative density or specific gravity of a material is actually the value of its density in gram per cc, because water has 1 gram per cc. So more precisely, it is water at 4 degrees C. Water's temperature varies with density or vice versa.
Hello, sir.
Yes.
Yeah, the water remains ideal at all the temperatures.
Yes. Unless we subject it to extreme temperature. So obviously we are talking about something in the range between 0 and 100 degrees C.
Okay, sir. Understood.
Okay, so next let's understand how the pressure gradient
Sir,
actually
sir,
occurs.
sir.
Yeah, what happens?
Last line, last line. Just
Okay, write down fast, please.
yes. Done, sir.
Okay, done. Now let's understand what actually causes the vertical pressure gradient, and you'll realize it's nothing but gravity. So for that, all we have to do is apply simple Newton's laws type of concept to a volume element of liquid. Okay, so what we mean by volume element of liquid is that within this stationary volume of liquid or this stationary body of liquid, okay, if you consider an imaginary cylinder of liquid like this, so it's not like it's a separate body. Okay, it's within that this only, but we are considering its free body diagram. So within this, consider this volume element of the fluid, which is within its so-called body of fluid. So suppose this volume element has this vertical length of delta y, and it has a cross-sectional area of S. So it's in the shape of a cylinder. So it's cylindrical. Now let's understand the free body diagram of this volume element separately. And in the free body diagram, let us consider only the vertical forces acting on it to understand its vertical equilibrium. Okay. So within that volume of liquid, if you understand this cylinder of liquid, this volume element is at rest. So what is keeping it at rest? A combination of forces. It has its own weight. So why it is not plunging to the bottom like that and accelerating with G? Because something is balancing its weight. Okay. So if we make the FBD of the volume element, in our inertial ground frame, it is at rest. Okay. And we consider only the vertical forces acting on it. We'll consider horizontal also later, but right now we consider only the vertical forces. So what are the vertical forces acting on it? We can clearly understand that obviously it has its own weight. Okay. So the gravitational pull of the earth, write it as delta mg, where delta m is the mass of that part. So it has a mass of delta m. But there is also some force due to pressure acting from below. So the area below is S. So the pressure is P, the force should be P into S. So now if this coordinate is Y, then you can see this coordinate over here is Y plus D1. So here P is equal to the pressure at Y. Okay. So then there should be also some force because of pressure acting on the upper surface. So let's write that as P plus delta P into S, because now P plus delta P is the pressure at Y plus delta Y. Because pressure is varying with Y coordinate. So if I change the Y coordinate by delta Y, then the pressure should also change by delta P. Okay, so that's this. So now consider the vertical equilibrium. It's at rest. So net force should be 0. So the downward force, the net downward force should be balanced by the upward force. So you see that this gives us a result that delta P into S is equal to minus of delta mg. So first of all, what this shows us is that the pressure is decreasing as we go up. That is why delta P is coming out as a negative quantity. Now secondly, that volume element will have a mass, which is density into volume. So this is, remember, ideal fluid of density rho. So that volume element, its volume will be how much now? It will be cross-sectional area into the vertical height, that is delta y. So delta m will now be substituted as this. So the change in pressure into S is equal to minus of density into volume. So that's this into G. So from this you can see that the change in pressure is minus of rho into g into delta y. So in other words, the rate of change of pressure as you go up through a distance of delta y, the pressure reduces by a factor of minus 4. So this is why we have the vertical pressure gradient, which is of course negative, which shows that pressure decreases as we go up. Along the vertical, the pressure decreases. Okay. So there's a sort of proof or derivation of that. Okay. Now, likewise, we can also understand the horizontal pressure gradient, why it is 0, by now considering another volume element. Okay. We could have done it for the same one also, but we'll this time take a more conveniently oriented element like this. So another volume element now, this time this has a length along the x-axis of dx, okay, and its surface area is S. So now if we consider the second one, this is our second volume element. So if we consider this one, and this time we consider only horizontal forces are shown in it, because we have already accounted for the vertical forces situation earlier. Okay, so we've seen how vertical forces balance for any volume element. So now we want to see how the horizontal forces balance. So if this is the pressure, force due to pressure, now this should be P plus delta P. But here P is basically the pressure at some x coordinate. So P plus delta P is at an x coordinate of x plus delta x. So this is where P is pressure at x equal to x. Okay. And P plus delta P is the pressure at x plus delta x. So now we will see that this is at rest in the inertial frame. So again, forces should balance. So this delta P should be 0. Now this delta P is the change in pressure on horizontal displacement of delta x. So that is what is showing us that delta P by delta x is 0. Whereas this is what is showing us that delta P by delta y is a negative quantity. Okay. So basically what causes the vertical pressure gradient is gravity, and why there is no horizontal pressure gradient is because there is no horizontal equivalent of gravity for this kind of a situation where the tank is at rest in a ground frame.
Then
Excuse me, sir, what is IF there in
Inertial frame. Inertial frame.
okay,
Free body diagrams are also always labeled as the reference frame being inertial or non-inertial.
sir, can you please take it up for a minute? Yeah, thank you, sir.
Okay, done.
1 minute, 1 minute. Done, sir.
Okay. So now once we are clear about this concept of pressure gradient, now it comes down to be able to calculate the pressure at any given point. Okay. So how do we find the absolute pressure at a given point, since we know how to calculate the change in pressure on the basis of delta y and delta x? Okay. So let's talk about pressure, and by pressure P we mean the term absolute pressure. Okay. And also another term that we use called hydrostatic pressure, or alternately we also use the term gauge pressure or hydrostatic pressure. Delta P. Okay. So what are these two terms? How they are related to each other? Let's understand. So if we have, once again, any open vessel, okay, we're talking about any open vessel in which there is a certain quantity of fluid whose density is known to us, then we can easily calculate the pressure at any point inside by using the open surface as a reference point, because the pressure right at the open surface will be equal to atmospheric pressure. So that becomes our reference point. So because this is an open surface, okay, so the pressure at a point like this will be equal to the atmospheric pressure. Okay. Which is because that is the case at any open surface. So now if we consider any point inside the fluid, all we have to know is we have to know the depth of that point. If that depth of that point is h with respect to the open surface, and we consider another point which is at a horizontal distance of d or whatever. Now we can see here that delta P by delta Y is equal to minus rho G. So if we apply this equation to the points A and B, what we'll say is that the going from A to B, the change in pressure is PB minus PA, that is delta P. But going from A to B, the change in Y coordinate is minus H. So that should be equal to minus H. So this is when I'm going from A to B. Or if I go from B to A, I can also write this as PA minus PB divided by H. This is going from B to A. So B to A, I'm going vertically upwards. So delta Y is plus H. Okay. And final is A, initial is B. Whereas if I'm going from A to B, I'm going down. So delta Y is minus H. And I'm going to B from A, so it is final minus initial. So either way, I can use this equation or this equation below. Both of us will give us the same result, that the difference in pressure is like this, that pressure at B is equal to pressure at A plus rho GH. So this kind of gives us a general formula to find the pressure at any point inside a fluid. It will be the pressure at the open surface plus rho GH. So this is the general formula for absolute pressure P at the point B, which is at a depth of H below an open surface. If we don't have an open surface, then also we'll discuss how to calculate the pressure. But this is the most standard kind of situation. Now, additionally, we can see another thing over here, that the pressure at the point C will be equal to the pressure at the point. Okay, so there are two ways to understand this, because delta P by delta X is 0 and B and C are at the same horizontal level, okay, or same depth from A, from the open surface. So the pressure at the point C will be equal to the pressure at the point B. Now this principle that we have developed for this, now this applies to any situation regardless of the shape of a container. So even if we have a situation like this now, which I'm drawing on the side, if we have a container of some odd kind of shape, okay, our container can be like this, for example, or we could even have a situation where we have a tube which we have bent in an odd kind of way. And just attached it to the ground. Okay. So whether it is this one or this one, but if this is an open surface of liquid here. So this is an open surface. Okay. This is an open surface. And I have again labeled this point as A. And suppose vertically below it, I have another point B, which is at a depth of H. And at the same horizontal level, I have another point C, which is at a distance D. So same way over here, if this point is A, I have some point below it somewhere over here, directly below it, which is at a depth of H. And then I have any other point which is at the same level. So the same equations will apply everywhere. Here also PB will be equal to PA plus rho GH, okay, and PC will be equal to PB, and PA will be equal to atmospheric pressure. Here also the same thing. PB will be equal to PC equal to P naught plus rho GH, because the pressure at the point A. So this is regardless of the shape of the container. As long as we have some open surface as a reference point, we know the pressure at any point on the open surface will be the atmospheric pressure. So a point at a depth of H from it, it doesn't matter what the shape of the container, whether the point is directly below or it's like this third diagram that I've drawn, where I have this very, very strange kind of shape of a container. But if the vertical depth of the point B from the point A is H, or the vertical depth of the point C also from the point A is directly H, then the pressure at both those points will be equal, and they'll be equal to P naught plus rho GH. And this value of pressure that we calculate, that is called the absolute pressure. Okay, so this is a very important aspect of the application of concept of pressure gradient. Make a note of this, then we'll discuss further. Now, Udit, to answer your question, no, it is like, we could have combined the vertical and horizontal forces in the same free body diagram also, but then we would have to consider, like, instead of a cylindrical shape, we'd have to consider a cuboidal shape or something like that, and consider different surfaces, different pair of surfaces. So it is just for convenience that one time we have taken a cylinder and placed it such that the axis is vertical. Another time we have taken the cylinder and placed it such that its axis is horizontal. And we have done a calculation for the comparison of the pressure between 2 points at a horizontal displacement of delta x and 2 points at a vertical displacement of delta x or delta y. You can like combine both the diagrams and imagine that kind of cuboidal shape, and you'll see that combination of vertical and horizontal forces is zero. Hope you're understanding the point. No, the cylinder cannot rotate because that is basically it's part of the body of fluid. No? So the fluid is at rest. So that cylinder of fluid is also at rest. But it's like we can imagine any sort of cylinder. No? So one time we can imagine a cylinder which is having a vertical axis so that it's convenient to see the vertical forces acting on it. Another time we can consider a horizontal axis cylinder to consider the horizontal forces on it. Or we could have taken a three-dimensional shape like a cuboid and considered all the forces together. Okay. So then the horizontal forces would also have to be divided into two components, X and Z. But you would see again they would balance each other. So 6 faces of the cube, they would be in two pairs cancelling each other, but the vertical ones won't be cancelling. Always the vertical will be such that the below surface is experiencing more force due to pressure compared to the upper surface because it has to balance the weight. So that is what shows us that gravity creates the vertical pressure gradient. And because there is no equivalent of gravity along X or Z axis, so there is no pressure gradient.
Sir, can you explain the right part again? I was disconnected, sir.
Sorry, can you repeat the question, please?
Sir, can you explain the right one part again? I was disconnected.
Yeah. So what is happening here is that again you see A is a point which is on an open surface. So the pressure at the point A will be atmospheric pressure. B is at a point which is at a vertical displacement of minus h compared to A. So all these equations that we have written for the first one, they all apply to B and C again over here. So that's why the pressure at the point B in both the cases, when we apply these same equations that we've written on the left hand side, we'll apply them to the points ABC on the right hand ones also, and it will be exactly the same. And hence we get the same result, that the pressure at the point B will be equal to pressure at point C, which will be atmospheric plus rho g h, because they're both at the depth of h compared to the open surface.
Understood, sir. Thank you.
Done, sir.
Okay, so now let's see a simple calculation type question based on this. So just to give you, now we have to discuss about gauge pressure. Okay. So we saw that pressure at that point B in the above examples, they were P naught plus rho gh. So this was the absolute pressure at the point B. So for example, if the density is 1 gram per cc like a water and the depth is 5 meters and we take G as 10 meters per second square, then the pressure at that point will become atmospheric pressure plus rho gh. So typically we take atmospheric pressure as 10 raised power 5 pascals. So here suppose we are taking a approximate value of atmospheric pressure as 10 raised power 5 pascals. So you know the more accurate value is actually 1.01 into 10 raised power 5 pascals at sea level. And then of course it varies with the height of a position with respect to sea level. So anyway, so this will become now, conversion becomes important here. So 1 gram per cc will become 10 raised power 3 kg per meter. So this has to be substituted in SI unit. So 10 raised power 3 into 10 into 5. So you can see this will become 1.5 into 10 raised power 5 pascals. So this is the absolute pressure at that depth. So this is the absolute pressure at a depth of this much below the open surface. Now next we'll also talk about hydrostatic pressure. At the point B, for example, from the above example. So at any point like B from the above example, what is the hydrostatic pressure at that point? Hydrostatic pressure at that point is the excess pressure due to the presence of the liquid. So it is just rho gh. So it is basically the excess pressure. Had the liquid not been there, it would have been at atmospheric pressure. Okay. So it is the excess pressure at a given point compared to the normal atmospheric pressure due to the column of liquid above. So here the hydrostatic pressure at that point would just be rho gh. So it would just be 5 into 10 raised power 4 pascals. So this would be the hydrostatic pressure. So having understood this now, let's do an example question. So we have a situation like a U tube over here, like a small glass tube bent into a U shape. Not the video sharing website YouTube, but what we've done here is we've got water. But on one side, we've also got some immiscible fluid, like let's say kerosene oil, which is lighter than water. To this. Okay. So this is kerosene and it's got a density of 0.8 gram per cc, whereas this is water. It's got a density of 1 gram per cc. So if this distance of the, the height of the kerosene column is, let us say, 15 centimeters, and this level of the water here is, let us say, 8 centimeters, then we have to find sorry, we have to find what this height h2 is. So this is an example of the application concept of pressure gradient that we have discussed about. Just try this question out. So let's check out the answers, people. So one simple thing we can do is we can, for example, in this, we can apply the concept that 2 points at the same horizontal level within the same liquid should have the same pressure. So if we consider a point here and a point here, they should have the same pressure. So pressure at the point A should be equal to pressure at the point B. Okay. Now we introduce an in-between point over here, C. And we can see that the pressure at the point A is equal to pressure at point C plus density of water into G into H1. And pressure at the point B is equal to atmospheric pressure plus density of water into G into H2. And now further you can see that if you compare this open surface point with the point C, see pressure at the point C is atmospheric pressure plus density of kerosene into G into that distance D plus density of water into G into H1. So that should be equal to P0 plus density of water into G into H2. So this will give us what we require. Density of kerosene into D plus density of water into H1 should be equal to density of water into H2. So H2 should come out to be H1 plus this factor into D. So it should come out to be 8 plus 0.8 into 15. Okay. So it should come out to be 20 centimeters. Okay, so this kind of question is quite common at JEE Mains level, especially. Now let's see another type of situation.
Excuse me, sir, please, just a minute.
Sorry, was there some doubt?
Sir, please scroll it up. Thank you, sir. Done, sir.
Okay. Next, let's look at another interesting type of question. So we have two containers of this type. Now they have the same base area. But obviously you can see they have different cross sections. Okay? And they are filled with the same fluid up to the same height. So now we have to consider several different things here. Okay? So this of same density rho. This is container 1, this is container 2. So we have to compare the pressure at the bottom surface of container and 1 and 2. Okay. Then the net force applied by the fluid on the floor of on the bottom floor of container 1 and 2. Then we have to consider the weight of fluid in container 1 and container 2. And now the thing is, does there seem to be any contradiction? So that's something you have to figure out. Okay, in just a moment. So this is part of a very ancient philosophical problem before physics was invented, called the hydrostatic paradox. Okay, but physics actually explains it. So there is no paradox as such. Okay, but in ancient times, this was called the hydrostatic paradox. So is there a contradiction or a paradox? And how can it be explained? So if you feel that there's some kind of a contradiction, then what is the correct explanation for that? We'll just try this out. It's an interesting problem we'll discuss. Okay, so the solution to this is that, yeah, the volumes are different. Okay, but the thing is that the pressure at the bottom of tank 1 is equal to the pressure at the bottom of tank 2, which is atmospheric pressure plus rho gh. Okay, because they are filled up to the same level, as you can see. See clearly in the diagram that the vertical height is the same. So then what is happening is that force that is acting on this bottom surface is the same in both the cases. So these small force into area vectors, collectively they apply a net force like a normal reaction type of force. So they'll both be the same because the areas also are the same. So F1 will be equal to F2, which will be equal to this pressure into area, where this pressure is this thing. So as far as the liquid is concerned, how much force it's applying, it's like we'll write it as where this is a hydrostatic pressure. So the force applied by the fluid on each floor, that is the pressure because of the fluid into that area. Okay. But then you can also see one thing, that weight of fluid in container 1 is less than weight of fluid in container 2, because volume is less. So then you think that there is in fact a contradiction. If the weights are different, how can the force at the bottom be the same? Okay. So there is a very nice explanation for that. Just try to figure it out. I'll tell it to you in a bit. So how do you explain this difference? Okay. So that's the thing. So now if you consider a free body diagram of the liquid body which is present in container 1 and the liquid body which is present in container 2. So you can see that this weight is less than this weight. But this normal reaction force will be equal to this normal reaction force, because this normal reaction force will be equal and opposite to the force that these are applying. Concept of action reaction principle applying here. Okay. So one more thing you can see over here is that weight of the second liquid is equal to rho gh into K, but the weight of the first liquid is less than, which is equal to this normal reaction. In the second case, this weight is actually less than the normal reaction. So what is the explanation for this discrepancy? This was the paradox that the ancient people had before Newton's laws and classical mechanics and all was invented. Yes, very good, Yash. That's correct. Yash Bhavishkar. The explanation is correct. So what happens here is that the force due to the liquid acting on the side walls. So now that is like this over here. And notice that the force is increasing because the pressure is increasing. But here the force, because of the liquid on the side walls, they are upwards. So now when you consider the liquid body, it experiences a reactionary force because of the walls, which is like this. So here the side walls are applying reactionary forces like this, which creates a net downward force. Whereas here the side walls are creating reactionary force like this. Okay. So the explanation for this is that because the side walls also apply a net downward force. In container 1. But net force due to side walls equals to 0 in container 2. So this is the logical explanation of this so-called paradox. Okay, so we will just conclude this section with
Sir. Can you
yes.
please scroll up?
Excuse me, sir.
Yes.
Sir, what is the last letter of the last sentence? Net downward force in.
In container 1.
Okay.
And in just one I have written, not in container 1. So in case 1 over here, this is a container 1 situation. Okay. This is a container 2 situation.
Got it.
So
Got it.
this is the free body diagram of the liquid. Okay, so that's why the direction of the force with the walls is the reaction to this. The liquid is applying downward force, so the wall applies and the floor applies upward force. The liquid is applying sideways force like this on the wall. So the wall applies equal and opposite force like this into it. So another now standard example based on the application of this concept is if you have a cubical container, it can also be cuboidal, whatever be the case. Okay, and you want to calculate, and it's filled with liquid right up to the top. So you want to find the force due to hydrostatic pressure or the force applied by the liquid on the floor and on each of the walls. So in the case of the floor, we have to just do a simple multiplication because it's a uniform pressure. So if this is an open cubical tank, and its dimension is L by L by L, it is filled with an ideal fluid of density rho. So you want to find the force applied by the fluid on the floor and on any of the side walls. So on the floor, you can see the force that the liquid applies will be downward like this, part A, and that force will be a uniform pressure into the area. So this force will be uniform pressure, and by pressure we mean hydrostatic pressure, because we're talking about the force that the liquid is applying, not what the atmosphere plus the liquid is applying. So it becomes rho g L cube. But when it comes to the second part, you have to understand that on the side wall, like let's say we consider this side wall, this is on this side. The liquid applies a force in this sort of direction, but that is coming as a result of variable pressure. So this force has to be calculated by integrating pressure over area, because pressure is variable. Because the pressure varies with depth. So to do that integration, what we do is we can consider a thin strip, a thin horizontal strip on the wall, which is at a certain depth from the top. So here, at a certain depth, y, let's say, we consider a thin strip of thickness dy. So the liquid is present on this side. So at a depth of y, you know the hydrostatic pressure will become rho gy, and the side length is L. So the area of that strip is L dy, length into thickness. So the net force that is acting on the side wall is going to be integration of the force on all these strips. So integration of pressure over area, hydrostatic pressure, that is. So we take the rho GL outside. Now we have to integrate for all the strips from the top right up to the bottom. So this is also L, because it's a cube. Okay. So it's L by L by L, so like that. Okay. So this will be from y equal to 0 to y equal to L. As you can see, this will give us rho GL, y square by 2 limits 0 to L. So this force on the side walls will become rho g L cube by 2. It's exactly the half of the force that is acting on the bottom floor, because the pressure is variable. Whereas on the bottom floor, there's a uniform high pressure of rho gn. But here the pressure actually varies between 0 and rho gn. So that's why the force is becoming less. This is on each side wall. There is a horizontally outward force of this motion. Whereas this is the force acting on the floor. Okay, so these are two common types of questions, 2 or 3 common types of questions which are related to directly the concept of pressure gradient. Okay. So we'll conclude today's session here, and next time we'll see that as a result of pressure gradient, there is a property that liquids have of upthrust or buoyancy. That is, they apply an upward force on any object when it is submerged inside the liquid. And buoyancy or upthrust is the principle for flotation of objects, or for the fact that any object inside a liquid will have an apparent weight less than its true weight. So we will see the derivation of Archimedes' principle and its applications in the next lecture. And with that, we'll finish hydrostatics.
So not yet written, just a minute.
Sorry, what was your question?
I have not written, just a minute.
Sorry?
So wait for 1 minute. I have not yet written. I'm writing
Yeah,
the
I'm
class.
waiting.
Bye, sir. Thank you, sir.
Okay, that's it for today's session, people. Yeah, homework. Yes, you can start from HC Verma part 1 has a chapter called fluid mechanics. So you can do the first 12 questions from that, question 1 to 12.
Sir. Sir. Excuse me, sir. 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 Sir, are you there? Excuse me, sir. 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 Sir, are you there?